Okay, so let's start. Today we'll solve two questions from topology from the year 2022. So question number 22 and question number 24 we will solve. So let's first play the question number 22. Okay, so today we'll solve Gate 2022 mathematics question. This is the question number 22 from topology. It is saying that let's consider this 0 1 with T1 where T1 the subspace topology from R. So 0 1 is taking the subspace topology from R and T2 be any topology on 0 1. Then statement P is saying that if T1 is proper subset of T2, then 0 1 with respect to T2 is not compact. And the question Q is saying that if T2 is proper subset of T1, then 0 1 with respect to T2 is not housed up. Okay, then you have to say which options is correct. This is the 1 mark question, and for this is the NPTEL reference. This you can look into it. Okay, so let's first check whether P is true or not. Okay, so what is given first? Given that the statement for P is given that if T1 is a proper subset of T2, right? Then it's given that T1 is a proper subset of T2. Then we have to check that 0, T2 is 0, 1 with respect to T2 is not compact. So what is the meaning of this? This is the same as that saying that if you take the identity operator from this space 0, 1 with T2 to 0, 1 with T1, it is saying that identity map is continuous. Right? Why? Because if you take any open set means so take any open set here, it is so U is in T1 mean U is open. So as any open set is open in T2 means, and this is basically identity operator. So if you take inverse image, it will basically I inverse of U, which is again U, which is again open in T2, right? So if U belongs to T1, which imply U is also belongs to T2, right? So which means that identity operator is continuous. Identity map, not. So now we have to prove that this 0, 1 with respect to T2 is not compact. So let's assume, suppose 0, 1 with respect to T2 is compact. Then let's see what will happen. So we'll prove that basically if we assume this, so we'll prove that this is not compact. So we will get a contradiction. So we'll show that if we assume that this is compact 0, 1 with respect to T2, then this topology becomes the same. So let U is in T2, you take an open set in from topology with respect to T2, we'll say that this is also open in T1, which implies T2 means U is open, right, in T2. So then take the complement with respect to 0, 1. Let's define it A 0, 1 minus U. Then this is closed, right? Because U is open, so this is closed in T2, right? Now note that T1 is a subset of T2, as T1 is a subset of T2. And what is T1? T1 is the just subspace topology from usual R. So obviously this T1, because subspace topology, because R has house drop, R is house drop, so the subspace topology it will also become house drop. So obviously 0, 1 with respect to T1 is house drop. And as T2 contains T1, so means if you take any 2 points, then you will find open set from T1 which will separate these 2 points. So these 2 open sets also belongs to T2, means T2 is also house drop. So therefore 0, 1 with respect to T2 is also house drop. Right, because T1 is a subset of T2. And we have assumed that this is compact. So what we get, T2 is compact and house drop. So 0, 1 with respect to T2 is compact house drop space. So in a compact house drop space, every closed set is compact, right? So therefore, because A is closed in T2, so which implies A is compact in T2. So we get that A is compact in T2. Now because identity map is continuous and compact image of a continuous image of a compact set is compact, so as continuous image of compact set is compact, so because I is a identity is continuous map, so I of A, which is again identity, is compact in T1, right? In T1, because identity takes T2 to T1, so this is compact in T1 and T1 is a house drop, right? So any because compact set, when compact sets are closed, if compact sets are in house drop space are always closed, as 0, 1 with respect to T1 is house drop, so A is closed in T1, right? So A is closed in T1, which implies its complement is open, which implies U, which is the 0, 1 minus A, is open in T1. Okay, so we have start with, so means which implies U belongs to T1. So whatever opens, we have started with open set with T2, we have shown that this is also an open set in T1. But we have assumed that T1 is strictly contained in T2. So from here, so this implies that T2 is same as T1, but which is a contradiction, right? Which is a contradiction. Okay, this is, let me write therefore, which is a contradiction. So therefore, what is our assumption? That this is compact, so 0 1 with respect to T2 is not compact. So 0 1 with respect to T2 is not compact. Okay, so therefore statement P is false. No, statement P is true, right? P is true means it is saying that it is not compact, so P is true. Okay, now let's check the statement Q. It is saying that if T2 is a proper subset of T1, then 0 1 with respect to T2 is not Hausdorff. Okay, this time its T2 is still contained in T2. Right, so therefore again we have, so this is same as earlier. So we take the identity map. So now this time we will take it from 0 1 with T1 to 0 1 with respect to T2. Now this become continuous, right? Why? If you take, if U belongs to T2, which implies U is also belongs to T1, right? As, which is meaning that identity map is continuous, right? Now I assume that, let's suppose Zero 1 with respect to T2 is Hausdorff. Then again we will arrive at a contradiction, that we will show that these two topology become the same. So let's start with the open set with T1. Let U is in T1, which implies U is open in T1. So then let's take the complement. Zero 1 minus U is closed in T1. Right, and this is 0 1 with respect to T1. This is basically the subspace topology from the usual topology of R. So therefore this is both, so as 0 1 with respect to T1 is subspace topology induced from usual topology of so therefore J1 with respect to T2 is both compact and Hausdorff. G01 with respect to T1 is compact and house drop. So in a compact house drop space, every closed subspace, so this is a means in compact house drop space, closed subsets are compact. So therefore A is compact in T1. Now again, as early a continuous image of a compact set is compact as continuous image of compact set is compact. So I of A, which is again A, is compact in T2. Now we have assumed that 0, 1 with respect to T2 is house drop. So in house drop space, every compact subsets are closed. So as 0, 1 with respect to T2 is house drop, this is our assumption. So which implies A is closed in T2. So is closed in T2 means its complement is open, so which implies U, which is the complement of A, is open in T2 which means that U belongs to T2. So we start with the T1 and it's shown that it's in T2, and as obviously T2 is subset of T1, so this implies that T1 is same as T2. These two topology become the same, but which is a contradiction because it's given that T2 is, I think, a strict subset of T1, so which is a contradiction. So therefore we have assumed that 0, 1 with respect to T2 is house drop, so this is not true. So 0, 1 with respect to T2 is not house drop. So Q is also true. So therefore both the statements P and Q are true. That if T1 is a proper subset of T2, then 0, 1 with respect to T2 is not compact, and if T2 is a proper subset of T1, then 0, 1 with respect to T2 is not house drop. So therefore option B is correct. Both P and Q are true. Right? Okay. Yeah, yes. Any doubt or any questions? No questions? Then you can move on to the next question. Question number 24. Okay. Okay, so today we'll solve Gate 2022 question from mathematics. This is a question number 24 from topology. So let xn be R for each n belongs to natural number, and why is this the product of xn where n belongs to natural number, and we have n row y with the product topology where each xn is the Euclidean topology or of R, and define this delta. This is the diagonal, means all the term x where x is the real number. This is the diagonal set. So this we have induced with the subspace topology from Y. Then 4 options are given. You have to check that delta is open in Y, its delta is locally compact, delta is dense in Y, or delta is disconnected. Which one is correct? You have to check. And for this question, this is the NPTEL reference. This you can look at it. Okay, so let's try to solve this one. First option, delta is open in Y. The option number A. So we will show that this is not true. We will show that delta, which is the diagonal set x such that x belongs to R, is not open in Y, or Y is this the product of all R cross R cross R, this is with product topology. So suppose, assume, we'll prove this by contradiction. Suppose delta is open in Y. Then what will happen? So if open set is open, it's saying that if every point is an interior point, means each point has a neighborhood, open neighborhood, which will is entirely contained in these sets. Means, so which implies every point, suppose let's denote it by x bar, this x comma x. So every point will belongs to some open set U, which is entirely contained in delta, right, where U is open in Y. And what is Y? This is the product of xn. N belongs to natural number, or xn's are basically the real line for all n. So U is a open in this product space, so means U, and with respect to product topology, so therefore how U will look like? U will be some U1 cross U2 cross dot 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 UK cross, and after finitely many, these are all R, right? So for some K, where this Uy for I equals to 1 are open in R for I equals to 1 to K, right? So this is the basics open sets in the product topology. Now we claim that this U1 will be singleton X. Claim this U1 will be singleton X. So suppose if not, then what will happen? If not, then so there will be some another element, there exists Y in this open set U1 such that Y will be not equals to X, right? There will be exist another point different than X, other than X. So if there is such y, then because this u is entirely contained in delta, so u1 if it is contained, then take this point, take y, x, first quadrant will take this. So this will belongs to also, right? This will belongs to u1 cross u2 dot 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 uk cross r cross dot dot dot, right? So this is the u which is again contained in, and this is contained in delta, right? But this type of points does not contain in delta, right? This is a contradiction. This is not true. As y not equals to x, right? This is not true. As y not equals to x, right? Because diagonal contains all the points which has all the same coordinate. So this is not true, means this u1 does not contain any other point other than x. So therefore our claim is true. Therefore u1 is basically just singleton x. And what is u1? So these ui are the open sets in R, right? And we have get u1 to be the singletons, which means, which is same thing as saying that u1 is, which is this singleton, is open in R. But this is not true, right? This is a contradiction. But why this contradiction arises? Because we have assumed that delta is open in Y, right? So which is a contradiction. So we have arrived this contradiction because of the assumption that this diagonal delta is open in Y. Therefore delta is not open in Y. Okay. So option A is not correct. Delta is not open in Y. Now let's check in option B. It's saying that delta is locally compact. Okay. So we'll show that this is true, means delta is locally compact. Let's recall the definition of locally compact. So a space X is called locally compact if there exists an open set U and a compact set K such that X belongs to U which is contained in K, right? So each point has a neighborhood which contain an open set, or each point is contained in an open set which is again contained in a compact set, right? So this is the definition for locally compact. And now we will use one more fact. Let's write it, or result. Saying that it means locally compactness is a basically topological property. What is this? locally compactness is topological property. What is the meaning of this? Means it preserves a local compactness is preserved under homeomorphisms. Means if f from some space x with topology tau 1 to x with respect to topology tau 2 is a homeomorphism, and x comma tau 1 is locally compact, then y comma tau 1 is locally compact. Right. So if there is a homeomorphism within two different spaces, so this is y. Then if one is locally compact, then other one will be locally compact also, if there is a homeomorphism. So this is the meaning that this is a topological property. So we'll show that this delta is homeomorphic to the some different space which is locally compact. So therefore this will be again locally compact. So let's claim. So R is basically homeomorphic to this delta, or R is homeomorphic to delta. Our delta is given the product topology, right? So what is, let's define this map R to delta, which is this basically the diagonal. So x goes to this x comma, right? So if we can show that this is okay. Now so if we can show that this is a homeomorphism, then then we can. So let's check the homeomorphism property. So let's use one theorem here. So for that homeomorphism, we have to show that f is continuous, this is bijective, and inverse is also continuous. Let's write down one theorem. For the continuity, we will use this theorem. F is continuous. So this is continuous. This is the one theorem for the product topology, that if let f from A to some product space alpha belongs to J x alpha, or this is given the product topology. And suppose f of A is sent to this f alpha A, where alpha belongs to J, and where each alpha is a map from A to x alpha. Then f is continuous if and only if each coordinate functions are continuous. Each functions F alpha is continuous. Right. So we'll use this theorem to prove this one. So what is F in our case? F is a map from basically R to this space, right? R to delta. F of x, which is x comma dot dot dot, right? So let me denote it that suppose f1x, f2x. So fnx is basically x for all n belongs to n. And fn is a map from, so note fn is a map from R to R. Fn of x equals to x. So this is clearly continuous for all n. This is basically identity map. Each fn's are continuous. So by the above theorem, F is continuous. So F is continuous, is fine. Now bijectivity is also fine. F is bijective. F is bijective. Right, because why F is 1 1? F is 1 1 basically. Suppose f of x equals to f of y. So what will happen then? X dot 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 equals to y. So each coordinate will be y, which implies x equals to y, right? And why f is onto? F is onto also. Because this is by definition onto, right? If you take any point, it will look like some. So let's z in this delta, which implies z will be some y dot dot dot. So then f of y will be z, right? Implies f is onto. Y is in R. So bijectivity is fine. Now inverse. So inverse is well defined. Then F inverse is a map from delta to R. It will basically take this x dot 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 to x. So F inverse is also continuous. How to solve this one? So for that, this you can see basically that now define that's the projection map. So let's define. Suppose projection from, suppose let define pi 1 from product of xi, I belongs to sub index set to x1. So what this is the product topology. So pi 1 is projecting this pi 1 of x1 x2 this it will only project the first coordinate x1. Then pi1 is continuous, then each projections are continuous, then pi1 is continuous. Why? Because pi1 inverse of, suppose take open set u1, it will be some u1 cross this x2 cross x3, right, which is open in this, right. xi. So pi1 is continuous, and basically this F inverse is restriction of this projection to, now in our case here F inverse is basically the restriction of pi1 to this set delta. So pi1 basically defined from xn here. So let me denote these are to be xn, then it will be because consistent with right. Then pi1 basically the F inverse is the restriction of pi1 to this. So this is basically map from delta to R. And as pi1 is a continuous and restriction of a continuous map is continuous. So this is again a theorem. If f from x to y is continuous and A is subspace of x, then f restricted to A, which is mapped from A to y, is also continuous. So therefore this F inverse is also continuous. Therefore F inverse, which is mapped from delta to R, is continuous. So we have got that F is a continuous, F is bijective, and F inverse is also continuous. So F from R to delta, so this is this set. What is the map? X goes to this x, this is homeomorphism. Now as we know that R, this is locally compact, as we know R is locally compact. Why R is for any point, suppose, so why this is locally compact? For any A in R, A is contained in some CD, right, which is again contained in C to D. And this is compact and this is open, right? And as delta is homomorphic to R, so therefore delta is also locally compact. Also delta is locally compact. By the earlier theorem, this theorem, right? This result, by earlier result. Okay, so this is the option B. So option B is correct. The delta is locally compact. Now option C, this is saying that delta is dense in Y. Let's check this one, that delta is dense in Y or not. So we'll show that delta is not dense. We will show that delta is not dense in Y. Okay, so here we need a one result. Let me write. So we'll show that delta is closed first. Then we'll show that this is not dense. So for this we will suppose let X is housed up. So let here we have what we have, the delta is closed if and only Y is, suppose this product of n belongs to n, this is xn, where xn is some same, right, x for all n. Then suppose this is with respect to product topology. Then delta, so let's define first the same as early diagonal. Delta is closed in Y if and only if this x is housed up. Right. So in our case, this is the R. So here Y is basically this product of n is xn, and xn are basically R for all n, and R is housed up. Therefore delta is closed. Now we will show that this delta is not dense. So what is meant by dense? So let me write the definition. A set, suppose C is dense in X if C closure, this is a closure of C, equals to X, where this is the closure of containing C. or intersection of all closed sets containing A. Intersection of all closed sets containing C. So a set is called dense if closure is equals to the whole space, whole topological space X. And also this is one result. If A is closed, then closure is the same of that set. This is one result. So you have to show that delta is, we will show that delta is not dense, means we will show that delta bar is not the whole Y. Now we have proved that delta is closed in Y, as we know, we have shown delta is closed in Y. So delta bar is same as delta, and we'll show that this is not equals to Y. And note, take some point, this point 1 2 3 4 dot 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 like this. So this does not belongs to in delta, right? So this is does not belongs to delta, but this is in the Y, and this, but this 1 2 3, this set is in Y. So therefore delta bar, which is again delta, not equals to Y, right? Implies delta bar is not equals to Y. Implies delta is not dense in Y. So therefore option number C is not correct. Delta is not dense in Y. Okay, now option number D, it's saying that delta is disconnected. Again we'll solve so that this option number D is also not correct. So D, we will show delta is not disconnected. Means we will show that basically delta is connected. Basically we will show delta is connected. Definition of connected. A space X is said to be connected if there does not exist a pair U B of disjoint non-empty open subsets of X whose union is X. So this is the definition of connected. And if X is not connected, we will call, otherwise X is called disconnected. Okay. So we'll show that this diagonal set delta is connected. So for this we will again this theorem. So let me use this theorem. Let me call it this theorem to be star. Which is theorem from part B. From theorem star of part B, we know this map there we have defined it from R to delta. This is the diagonal set. X goes to this is continuous. Right, so we know f is continuous. And this is basically the delta is the image of R, right? Also note image of f under f. So this is the delta. And let me write one more result. So here we know that f is continuous and we know R is connected, right? And there is one result that this continuous image of a connected set is connected. And writing so therefore using this one, as we know R is connected and delta is basically image of R under F, and F is continuous. So this is basically continuous image. Under F, which implies delta is connected. So therefore option D is also false, right? So therefore what we have got, the delta is open, so this is not open, this is A is false. Delta is locally compact, it's true. Delta is dense in Y, it's not true. Delta is not dense in Y. Delta is disconnected, it is also not true. So only B is true, that this diagonal set delta is locally compact. Okay. Okay. So any doubt or any questions? Okay, then we can stop for today. We'll meet in the next week. Bye. Okay, thank you. Bye.